Hello, welcome to a video about light as an electromagnetic wave. Definitely patting myself on the back for the aesthetic of this title slide. I reckon it's my best work yet. So just a couple of learning intentions for this video. Light is the visible part of the electromagnetic spectrum, a spectrum that also includes radio waves, microwaves, infrared and ultraviolet radiations, X-rays and gamma rays, and electromagnetic waves can be modelled as a transverse wave that can travel through a vacuum. There's no specific success criteria for this video that we haven't already kind of covered. It's just an extension of what we have covered, as well as information that's necessary to understand our study of light. So you need to know that electromagnetic waves are transverse and mutually perpendicular. So if you recall from some of our other videos, transverse means that the vibration of the wave will travel perpendicularly to the direction of the wave's propagation. So if you've got a wave that's travelling in this direction, the particles of the wave will travel perpendicularly to the direction of travel. Electromagnetic waves are made up of an electric field that oscillates at 90 degrees to a magnetic field, and because we live in a 3D world, even though they're oscillating at 90 degrees to each other, there's still a third direction that they're both oscillating at 90 degrees to, and that's the direction that the wave travels in. So you've got a little schematic here that shows the magnetic field maybe in the, what would that be? That would be the Y plane, the direction in the X plane, and then the electric field is in the Z plane. Electromagnetic waves don't require a medium to travel in, so they can travel in a vacuum. So even if there's no air particles, electromagnetic waves can still propagate through that vacuum. So this is unlike sound waves, which require those particles to be vibrating in order for the sound wave to propagate. I think I showed you the video of like an alarm or something, or a bell ringing in a vacuum. Once all the air has been removed and you can no longer hear the alarm or the bell going off, and it's only after like the valve is opened again and air can flow back in that you start to hear the noise again. Electromagnetic waves also carry energy between locations, so they carry energy but there's no transfer of mass, which is how waves work. Just before I move on to the next slide, I'll just clarify that mutually perpendicular means that the electric and magnetic fields are oscillating at 90 degrees to each other, so they're mutually perpendicular to each other, and then obviously the transverse means that they're travelling at 90 degrees to the direction of wave propagation. Here are a couple of GIFs of how electromagnetic waves propagate. So the bottom shows the mutually perpendicular and transverse nature of electromagnetic waves. So the electric field and the magnetic field are oscillating at 90 degrees to each other, and then they're both oscillating at 90 degrees to the direction of the wave's propagation. The top GIF shows an oscillating charge, and it's this oscillating charge that produces the electric field, which in turn produces the magnetic field, and you'll look a little bit more at that in stage 2 physics. So essentially a changing electric field produces a changing magnetic field and vice versa. So that's kind of how the waves propagate, but we'll look more at that next year. So in terms of the electromagnetic spectrum, Frequencies can range from 10 to the 0 hertz, which is the same as 1 hertz, all the way through to 10 to the 23 hertz. The electromagnetic spectrum is divided into frequency bands, so radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. So each of these bands have different properties, or the waves in these bands have different properties, and that includes how they're produced, their interaction with matter, and also their application, so how we can harness and utilize these types of waves. One thing that I will mention, and I'm going to talk about it on the next slide anyway, but I'll mention it now, is that all electromagnetic waves have the same speed, and that speed is equal to the speed of light, which is 3.0 by 10 to the 8 meters per second. Sorry for the dodgy 3 there. So it doesn't matter what type of electromagnetic wave we're talking about or what frequency, they'll always have the same speed. So to reiterate, with our wave formula, the speed of any electromagnetic wave is going to be equal to c, or 3.0 by 10 to the 8 meters per second. Hopefully you can see that this rule here is simply just the wave formula, and we've just subbed in c for v, the wave speed. C is measured in meters per second. Frequency, hopefully you remember, is measured in hertz, and wavelength is measured in meters. And this applies for all electromagnetic radiation. So a couple of examples. What is the frequency of visible violet light if its wavelength is 400 nanometers? So we've got the wavelength here, 400 nanometers, or 400 by 10 to the -9 meters, and it's visible violet light. We want to find out what the frequency is. We use our wave formula, which is C equals frequency multiplied by wavelength, and we'll rearrange to get frequency as our subject, which will be the speed of light divided by the wavelength. This will be equal to 3 by 10 to the 8 meters per second divided by 400 by 10 to the -9. If you pop this into your calculator, you'll end up with a frequency of 7.5 by 10 to the 14 hertz. So that is the frequency of visible violet light if its wavelength is 400 meters. So the important thing to remember is, even though we've only been given one value here, the wavelength, we already know that for any electromagnetic radiation, its speed is always equal to c, which is 3.0 by 10 to the 8. Next question, what is the wavelength of light with a frequency of 6 by 10 to the 14 hertz? So in this situation, we're given the frequency, which is 6.0 by 10 to the 14 hertz. We want to know what the wavelength is, and we know that the speed is equal to c. So our wave formula is c equals frequency by wavelength. we're going to rearrange to make wavelength the subject, so it'll be speed of the wave divided by frequency, and this will be equal to 3 by 10 to the 8 divided by our frequency, which is 6 by 10 to the 14 hertz. And if you were to pop that into a calculator, you would end up with 5.0 by 10 to the negative 7 meters. So that is the wavelength of light with a frequency of 6.0 by 10 to the 14 hertz.